welcome back. In this final application for this week, we will be looking at something which is different from all the 3 examples that we saw before. This is the solution of differential equations using neural networks. So, as you know, in almost all of engineering and science, most of us encounter differential equations in one form or the other. Now, these differential equations can either be ODEs, ordinary differential equations, or PDEs. Now, here is the question: can neural networks be actually used to solve ODEs and PDEs? Now, unlike the other 3 applications, I will not make a separate video for this just to describe the problem and then ask you to think about it, because this is actually honestly it is a very clever idea, and it is unlikely that one would think of it on one's own. In fact, it will look very different from almost everything else that we have discussed in this course, because you will not clearly see a training set, a testing set, a validation set, etc. So, please do remember this as I go over this example. The idea behind this example goes back to a set of papers by Lagares et al. This is late 90s, early 2000s. If you just put Lagares neural networks, you should find these publications. The application that I will be discussing right now is by a set of researchers from Brown, Ricey et al. As you will see, I will show you the paper shortly, and this has just been published last year. So, this is extremely recent. The reason for including this, A, of course, is ODEs and PDEs affect us completely within engineering and science. B, this is very different from the other applications that we have seen so far. In fact, this is not a surrogate model. Okay. So, remember in the CFD video, I had shown you how actually differential equations are discretized, or using the finite difference method we kind of make an approximate equation. Now, in this case we are not doing that, you are using an entirely different method. You are posing every ODE or PDE as convert this into an optimization problem, and you will see this extremely clever way of doing this. Okay. Like I said, the original idea was by these researchers, and I would request you to look at it in case you are interested in this field. I do think that this is going to get very important, and before I describe the problem, I would like to talk a little bit about what the importance is. So, remember that when we were using finite difference method or whatever method that we had used to generate the CFD solutions, this was still in the usual way. Now, in this case, maybe using neural networks you can automatize the whole thing, and the neural network can both solve as well as learn from the solution. So, this is moving towards full automation of solving differential equations using neural networks. That is, first you solve it using neural networks, and then you make a surrogate neural network for this original neural network. This can look a little bit confusing, but I do think that this is going to be slowly, it will start seeping into the mainstream of a lot of CAE solvers. So, that is the reason for discussing this. So, let us take a very simple differential equation. So, let us say I have the differential equation d square t dx square. In fact, let me change this variable to something else. Let us call it d square u dx square plus say a du dx equal to b. Suppose you wish to solve this, you will also be given 2 boundary conditions without which you cannot solve this, it is not a well posed problem. So, let us say u0 equals u0, and let us say this x lies between 0 and 1, and you have 2 boundary conditions. Now, you can do this in multiple ways. Of course, you can do this analytically. Okay, this equation is solvable analytically, you would have seen this, it is a second order linear differential equation, or you can do this numerically using the kind of method that I discussed. Now, there is a third method that uses neural networks, it is a clever method. which is as follows. We assume that U is some neural network that takes in X as input and gives U as output. Okay. Just to make this clear diagrammatically, the neural network will look like this. X is the input, of course, typically we have a bias unit, and then something happens here. This is the neural network. It could be, in case you are getting unclear, we can simply assume it is a single hidden layer. And after all this, you get U as output. Okay. Now, why is it possible? Regardless of which differential equation it is, we know from the universal approximation theorem that I can always approximate the solution of U arbitrarily closely by a neural network. Okay. So, because that is possible, I can always assume that U is some neural network of X. Okay. Now, how does that help us? It helps us because suppose I postulate. So, suppose I decide, just like we did with the theta b m x example, I take X, let us say I put in 10 neural network 10 neurons, and here is U. Okay. Whenever we do this, we are actually writing a full functional form for U. How is that so? Let me take a simple example. Let us say X is there, and for now I am going to forget the bias unit. Let us say there is a hidden neuron A, let us say this is my simple model, and then I have U. Okay. So, what this says is A1 is of course sigmoid of some W x, and U is, let us say this is a linear layer and this is sigmoid in it, and U is some other W2 times sigmoid of W1 x. Okay. Now, suppose I want du dx, I can actually calculate this analytically. I can write this as W2 sigmoid prime W1 x times W1. Similarly, you can calculate d square u dx square, etc. Okay. That is, all derivatives, this is the key point, all derivatives of U with respect to the input x can be found. Okay. Now, you might think that this is possible only because I had a single hidden neuron. What if I had 10 hidden neurons, or worse still, what if I had multiple layers of hidden neurons? Okay. Even if you have multiple layers of hidden neurons, through backprop you can always find out d of the output with respect to d of the input, just like we did d of the loss function with respect to the weights. You can similarly find out using the same backprop idea. This is called automatic differentiation. So, same idea you use output with respect to input. In fact, Tensorflow has inbuilt functions that do this. Okay, I will show you the function, I will show it to you from the paper, how they actually did it. So, the point is this: the moment you give a neural network, we can find if U is a given neural network of x, we can find U prime of x, which is du dx, U double prime of x, etc. Okay. Now, this makes things easy for us. Why? Because now, instead of saying I am solving this equation, I will pose the problem as follows. d square u dx square, let us call, since this is an approximation, we will call u hat, okay, just like we did y and y hat. So, the original is u, the neural network predicts u hat. So, what u hat do we want? We want u hat to satisfy d square u hat dx square plus a du hat dx minus b equal to 0, but obviously it is not going to be exactly 0. So, what do? I square it and say minimize. Okay. So, this is an extremely clever posing of the problem. Instead of saying I solve d square u dx square plus a du dx minus b equal to 0, I say minimize this, and obviously the actual minimum will be only for the exact solution, because that would be 0. Now, what you will get in practice of course is something a little bit closer to 0, but it will not be exactly 0, because our neural network will in general not approximate this, not get the exact solution. Okay. Now, this tells you that this is the cost function that you have to minimize, and the moment you put in the neural network, it can, for a given w, let us say you initialize with some w's, let us say w1 w2 in the example that I gave, you put that in, calculate this from the neural network, because w1 and w2 are given, you can actually do forward prop, calculate this, calculate this, calculate this, try and minimize, do gradient descent. This is our new cost function. But if you have been paying attention so far, you will notice that this is not sufficient, because we have this condition also. What do we do about this? This will just satisfy the ODE, but it will not satisfy the boundary conditions. Turns out that is straightforward also. All you need to do is add that also to the cost. How do you add it? You say u hat of 0. Remember, if I give 0 as input in this neural network, it will find out a u hat, okay, minus u 0, which is supposed to be the exact solution, plus u hat 1 minus u 1 square. So, this total thing all put together is our loss function. Okay. Please think about this. This is an extremely clever posing of the problem. So, that differential equation and the boundary conditions have all been put together as a single optimization problem. So, the ODE has now been converted to an optimization problem, and after this it is simply a solution. Okay. So, how will you solve it? You try various values of x, that is, let us say you have 0, you have 1. Now, as it is posed for each x, so you will put x equal to, let us say 0.1, run this, that will give you a residual, or that will give you a loss, 0.2, that will give you a loss, so on and so forth. So, let us say we put 10 points and say at these 10 points I will calculate how much this is and I will try to minimize. That is it. There is no training set really. If you wish to, you can call this the training set, that is any arbitrary x point, but this is not supervised in any way, because I am not giving you a label. All I am telling you is this is the function to be minimized. I can automatically find out the values of this function there, this differential equations residual there, add it together and try to minimize it. Okay. So, this is the formulation of the problem. We will see you can do this obviously for PDEs, ODEs, anything. This is just a fantastically universal method of solution, and I will just show you Ricey et al., who are the authors of this paper, the solutions that they have found out. I will show you those for a couple of problems. So, let us see those. Okay. So, here is the link to the paper. It is an archive, well, it is now been published in Journal of Computational Physics, I think this year only 2019, but you can search for this. They call this physics informed deep learning or physics informed neural networks, PINN as they call it. It is physics informed because unlike all the previous cases that we saw, remember when we were doing the CFD solution, computational fluid dynamics solution of a car, etc., I had no knowledge about the physics, only the training set had knowledge about the physics. My deployment was simply a CNN, it took it as an image. Here the neural network is trying to impose the differential equation. Okay. So, that is why it is physics informed. The differential equation obviously comes from physics. Okay. So, this is the paper. I would highly recommend that you read it. It is extremely well written. It is very, very well written, very clear paper. They have their code put up on GitHub. The links for their code are actually here. Okay. And the code actually works as advertised. Okay. Of course, there is a Jupyter notebook. You can just open it and run it. I will show you some outputs from their paper, but I would highly recommend that you go back to the original paper and take a look at it. The archive link is given just in case some of you do not have access to JCP. They have actually very kindly put up their original paper on archive also. Okay, so, here is the equation that they have tried to solve in the paper. This is of course a partial differential equation. This equation is known as Berger's equation. Okay. You will see ut plus ux minus uxx, this is what is called the viscous of Berger's equation. Okay. Now, unlike simple ODEs, you have to give a little bit more these. Okay. So, this has both x as well as time. So, what happens is at some initial time t equal to 0, you know what the function looks like. So, in this case they have said that at time t equal to 0, my function looks like sin x. The question is, what does it look like at a later time? So, this is called marching. Okay. You start from t equal to 0 and you slowly move forward in time, and they want the solution from t equal to 0 to t equal to 1. Okay. The postulate is as follows: u of x comma t is a neural network that takes x and t as input and u as output. So, x, t, neural network, u. If I remember correctly, they have tried various number of layers and various number of neurons. For this problem they have, if I remember correctly, 20 layers, no, I think it is 9 layers with 20 neurons each. Okay. So, please do refer to the paper, I might be wrong on this number. Okay. So, the boundary conditions they have given, this is what is called the initial condition. Apart from that, you will have to say that as you move forward in time, okay, this is x, remember, as you move forward in time, what happens at the boundaries. Okay. So, what they have said is at the boundaries are fixed at 0. Okay. So, x goes from -1 to 1 and both the boundaries are always fixed at 0, and we want to see what the flow solution evolves like. Physically we have some idea, but I am not going to discuss this because very few people watching this video would actually have directly any physical knowledge of the equation. Okay. Now, going back to the original idea, if I pose it this way, then my loss function is as follows. I will say minimize ut, which is now a neural network with respect to t. Remember, it takes x and t as input. I can always find the derivative of u with respect to t using backprop. Similarly, u with respect to x, backprop, and suppose I want uxx, I do backprop once, backprop once more. Okay. When I say backprop is a slight abuse of notation, it is actually what is called autograd or automatic differentiation, okay. But it works very, very similar to how our backprop works. Okay. So, ut plus ux, let me call this coefficient mu, so because it is just a constant, minus mu times uxx. This has to be 0, but instead I will square it and say, of course, I will assume this is u hat. Now, the other condition is when I set t equal to 0 and x is x, this function should become minus sin pi x. Again u hat might not satisfy it. So, I will say u hat u x plus sin pi x square. Similarly, I have one more condition here, u at t minus 1 should be 0, u at t 1 should also be 0. Okay. So, all these added together will give me my loss function. So, every guess that you have for the weights automatically guesses some connection between x and u, okay. And when you differentiate that and add these conditions, you want to minimize the total loss of that, which gives you gradient descent for the weight. Okay. So, very clever sort of method of implementing it. That is basically what they have written in their paper. This section is right from there. Instead of calling it u hat, they have called this f is the residual, that is what remains when you do this calculation. If you want just to be consistent with our notation, you can put it as u hat. Okay. They have actually given a Python code snippet in their paper, but they actually have given their full code also online. So, this is actually a good problem to start with. Actually, some of you might find it very interesting to start with this in case you have ever worked with differential equations. The code is extremely well written, very well written, very clear. So, that is one other reason that I would like to recommend it. Okay. So, here is just some sections that they have, the definition of how they have defined the neural network, and also how they have found out the gradient. So, you see here, this here is del u del t, this is del u del x, and this is a gradient of a gradient they have found out. This is automatically available within TensorFlow. Okay. So, once you do that, here are the solutions, here is the contour of u. Okay. So, here you see, here is where they have given the initial condition, these are boundary conditions here, okay, minus 1 to 1. Okay. And apart from this, remember the ODE example that I gave, you will have to actually take lots of points between these, they call collocation points. These are the points where you want to make sure that the differential equation is satisfied. Now, one other point of detail, you want to make sure that you take mean loss. Okay. So, obviously, if you have lots and lots of point on the inside and only a few points on the boundary, you will get a lot of loss from inside the domain and only very little from the boundary. In order to avoid that, what they have done is to actually take mean of these points, mean of these points, mean of loss of these points separately, and once you do that, it is a little bit balanced. There are still some questions left. For example, people in my group are actually trying to find out, there are small problems that still remain within this PINN, and we are trying to handle that within my group. But apart from that, it is a very well written code and very intelligent scheme. Okay. So, once you do that, you see here the solution. Notice here that blue is the exact solution, which is obtained from the kind of finite difference method that I told you. Actually, in this case, we even know the analytical solution kind of. Okay. And here is the prediction, this performs extremely well. The code that they have given performs extremely well. It turns out that finite difference actually will have some trouble for portions of this code. PIN tends to do this extremely well without any trouble at all. So, this is a very impressive performance. They have actually gone on to do some solutions of Navier-Stokes, some inverse problems. Unfortunately, we did not have time to discuss that. That is a very big use of neural networks that you can put it to in order to do inverse problems. Now, apart from this, they have also looked at Schrodinger equation. So, within physics, Schrodinger equation solutions are required within quantum mechanics. So, this is a solution of a Schrodinger equation. Again, this was split into real and complex part, imaginary part, etc. Again, this is an initial value problem x t, very similar. You can see once again that the exact solution and the predicted solution are extremely good. So, in summary, this is a very novel application of neural networks. One should say it does not really have a clear training set, testing set, no clear supervision of data at all, not clear, it is not there at all. There is no supervision really required, you just give the differential equation and the loss term is figured out from there rather than from a labeled y hat. All you do is make sure that your u hat satisfies the differential equation in a least square sense. I expect that the applications of this will grow with time. I do know several groups in the world are actually working on this, and hopefully we will see good developments within even commercial software using this kind of idea in the future. So, what we have done in the past 4 videos is 4 different applications. One is sort of a vanilla very simple neural network application, 2 very modern CNN applications within CAE, computer aided engineering, and the last one which I expect to grow more and more in the future. Actually, the last 3 applications I expect to grow more and more in the future. Now, that being said, we did not do several applications in this course, obviously due to paucity of time and also the kind of medium that we are using. We can do different things if people are here in person and if you had good computational resources. One important thing that I talked about in the last video is something called conv-LSTM. This is just to change from here. So, conv-LSTM is just sort of a image based RNN. One of the problems we had given in the exercises was, with a scan, if you have multiple images and you have a video instead of a simple static image, how can you do RNN with that? So, one way is to take an original image, the final fully connected layer is actually small and this can go into an RNN, but this is called a CNN LSTM. Okay. A conv-LSTM is slightly different. Wherever you had products such as, remember WH plus UX, you actually change it to a convolution. Once again, the basic idea is the same. You have a sequence of images. One of the first applications within our field for conv-LSTM was when in weather prediction, this is 2015, the basic idea was you use a sequence of radar images, okay, with which you can kind of predict the amount of monsoon and try and predict how this radar image will look like in the future. This is supposed to help in monsoon prediction, weather prediction, etc. I would encourage you to look at these terms conv-LSTM and put weather prediction, and you will find some good links there. The results are still preliminary. I know that Indian Institute of Tropical Meteorology, it is also called IITM, in Pune, they are also trying this. Several institutes within India are trying it, and of course worldwide people have been now trying to incorporate CNNs, LSTMs in order to make predictive forecasts about weather, rainfall, etc. Often you will find CNN LSTMs or other convolutional LSTMs being used in sort of trying to predict the next frame within a video, but that is not of great interest to us within, let us say, engineering. Engineering, we are more interested in, you have sequence of images and you want to what happens next in terms of practical things like rainfall, etc. Now, the sky is the limit for the type of applications that are there for all the techniques that we have discussed so far. I will talk briefly about this in the next video, but within this course unfortunately we had time for only this. I would highly encourage you to look at all the papers that I referred to and see the references within those papers, and also see who has referred to those papers later on, in order to get a very wide bunch of applications. Weather prediction, especially in the earth sciences, I just recently went to a conference and saw the vast number of the large amount of work which is being done in this area. Okay. So that is it for the applications for this week. I will summarize what all we have done in the course so far in the next video. Thank you.